Okay, so this is going to be chapter 9. And you can see that. We'll go over here. There we go. So we're going to work through hypothesis testing examples, and we'll do one of each type. So the very first one, I'm looking at this HT example blank file. I'll go to the mean pop var. Hopefully this makes a little more sense as we work through it, why I called it this. That worksheet, that first one. So this is going to be a situation where we want to do some hypothesis testing. We somehow know the population variance, even though we don't know the population mean. I said these are not the most likely scenarios, but we've got to walk before we can run. So let's say I start out and I assume, right, that mean is exactly equal to 32. I then scope. So what I'm trying to test for is it anything different from that? So instead of putting symbols, I kind of use this not equal to sign. If I wasn't as lazy, I would have like inserted the, equal sign with a cross through it. So here we've got, a two-tailed test. We could see a mean that's either above or below 32, and it would be evidence that it goes against that null hypothesis. So the first thing we're going to do is find the mean. If I can type using that average function. I'm just going to do BMI here. So I'm going to select that, hit enter. I'm then going to look, okay, what's my sample size? I can simply use the count function. So if I use that count function and select my range of data, it'll just say, okay, I'm counting the number of observations here. Okay. Now from here, I put the hypothesized true value of 32 up here. So you can kind of see like you could play around with this after the fact, but for now, we'll just start out with 32. So the first thing I'm going to do is calculate my test statistic, right? So let me actually accompany this. And so you should be able to see this now. So we want to calculate our test statistic or our, Z statistic. The way we're going to do that for hypothesis testing is we'll take the sample mean value we found, subtract the assumed true mean, divide by the standard deviation of our sample means, which is simply the variance of the data we sampled from over our sample size. So I think we had like what, 145. I think I gave you this was 60. Excuse me. And then this was our hypothesized true value of 32. We found, I forget what it was, 20. Let's see, 29.4. Right? So all it is a matter of plugging all those values in, right? Using Excel to be our calculator. There's no kind of built-in function for this. We're just going to say, okay, take our sample mean, subtract the assumed true mean. And I'm just going to use cell references here, but you could type that value in. I'm then going to divide by the square root of my population variance divided by my sample size. Hit enter. Oh yeah, close my parentheses for it. So I get about negative 3.88, right? I found a sample mean that was almost 4 standard deviations below what I assumed to be true. Now, I think here I'll play around this. Let's say, just to give us something a little more practical, let's say I make this population variance. That's not even, let's go even larger. Let's do 3,600, right? Yeah, we can use that one. And you can play around with this, doesn't really matter. I just want to point this out to you to really make it allow you to see something. So here I've got my test statistic of negative 0.5, right? So how will I find my p-value? Well, my p-value is going to be, I found this test statistic of approximately, I forget exactly what it was, like negative 0.5. I want to find the probability I found evidence that went against the null as much as I found, or anything that would go against it even more, right? However, for a two-tailed test, for every single value in this range, it was equally as likely I saw a value above that assumed true mean, and all of these would go against the null. So I can find the area in this left tail. I then need to remember I have to multiply it by 2. Okay? So go back here. There's a couple ways we can do this. The first is just, okay, I know that I've got a known population variance. I can use that standard normal distribution. So norm.s.dist. I have my Z value, my test statistic, I want to find the area to the left of, comma 1. So I want the area to the left, so I want it to be cumulative. This gives me the area to the left. We said the next thing I would have to then do is take this and multiply it by 2 to get my total p-value. Now I can do this in separate cells, or, just to make it easy, less than, I can also kind of just put it here at the front. Oops. So get rid of that. Now it's all just in one cell, but you can break it down if that's helpful. Now our critical value is going to be, well, before I do the critical value, the p-value approach I think is kind of easy. So we'll do our rejection decision. So this is kind of where I'll play around. You don't have to necessarily write this anytime I ask you for a rejection decision. You can just put if you reject or you fail to reject the null. And our p-value approach is we always reject if the p-value is less than alpha. So we've got our alpha set here, the 95% confidence interval. Alpha is going to be 0.05. Okay. So what we're going to test is, okay, if that p-value is less than 0.05, comma, then I know I should be rejecting. So put the word reject in this cell. So what am I testing to see? Is the p-value less than my alpha? If it is, so if that's true, what do I put in this cell? I put the word reject. If it's not, then I should be failing to reject. So now if I hit enter, okay, yeah, my p-value is not anywhere close to being less than alpha. So I should be failing to reject. Let's say we go back to the original variance, which was 60. Now I get a really low p-value, definitely less than alpha. Now I have the word reject in here. Okay, so if I set up everything with cell references, even if things change, like maybe I was told, oh, the population variance is actually this, I can kind of play around with that. Okay. Now, if I'm thinking about my critical value, remember, here's kind of where I was plotting my test statistic. The critical value is going to be the value, well, let me just draw this back out here. Save myself a little room down here. So we're thinking about, okay, where is the critical value that's going to give me alpha total in the tails? However, for a two-tailed test, we know that we're going to have two critical values, right? Because I could see evidence above or below the mean, and they would both go against that assumed true mean. So what I'm going to do is, okay, look, I want the critical value that's going to give me alpha total in the tails, but that means that I've got kind of like half of alpha in each tail. So to find this underlying Z value, this critical value, I need to use that a function in Excel where I know the area that I have in that lower left tail is going to be alpha over 2. So what does this look like in Excel? So we're going to go here. We're working backwards. We now know the area we want in the tail, so we're going to use norm.s.inv. If our alpha here is with the area we want total in the tails, in each tail we want half of alpha. So this will always, if I put alpha over 2 in this norm.s.inv, it's always going to give me my critical value for a two-tailed test. But the negative one, I have to kind of somehow indicate or remember, well, I have the same critical value on the other side. It's just going to be positive, so I can use that absolute value. Now I'm kind of showing here, oh yeah, I have two critical values here. Excuse me. All right. So it gets a little bit trickier if I want to make my rejection decision using the critical value approach, because really what I'm looking to see is this test statistic somewhere in this range, right? Here's my rejection region. If my test statistic is anywhere over here, I should reject. So what is that really saying? Well, I could find a test statistic that's positive, in which case I'd reject if it's greater than the critical value. But if I find a test statistic that's negative, like we did here, well, that's not going to be greater than a positive value. It's negative, but is it a larger negative value than my critical value? So what I'm saying here is it less than, but really on both sides, I just want to know, is that test statistic greater in absolute value? So that's the check that we can kind of use in Excel. So here, rejection decision, I say, okay, look, if the absolute value of my test statistic is greater than the absolute value of, and here we don't have to use absolute value since I already have a positive one, but right, if it's greater than this critical value, comma, put the word reject. It's in my rejection region. If it's not, put the words fail to reject. And now, hopefully, these will always kind of line up if I've done it correctly. And I can play around with, let's say I go back to this is 60. Now I'm rejecting in both. Why? Oh yeah, my test statistic is much larger than my critical value. My p-value is much less than alpha. If the population variance was a little bit higher, okay, nope, my test statistic is not greater in absolute value than my critical value, and my p-value is not less than alpha. Okay. So this is a two-tailed test. Now, you can also do it a different way. So I kind of showed you where you can find the area in the left tail, multiply it by 2. Oh, actually, I lied to you. This is not in this one. So that's kind of how I would approach these. And like I said, here doesn't matter which rejection decision you use, you should always be making the same decision. So the next thing we're going to do is look over here on this worksheet where I've got hypothesis testing for proportions. So looks like I've kind of got some of this already kind of built in. I'll go through this again. This, no surprise, I'm just using that count function, so it's pretty easy. Here, I've got my sample proportion. I'm just taking the kind of mean of this 1, 0 variable. So can't see, I think it was sorted. So all the ones are going to be, yeah, there's a lot more of the ones are down here. But this was, I believe, cigarette use data. So this was like, have they ever used, and I think it might have been e-cigarettes, which is kind of wild because like there's, like some that's not that wild. There's some 15, there's some younger aged individuals in this data set who are already kind of vaping. So that's great for society. But we're just interested in what the true population proportion of kids who are kind of ever have vaped in these lower grade levels. So I've got this hypothesized true value of 0.175, right? I want to know, is the proportion greater than that? So I'll assume the opposite is true, which is that it's less than or equal to that, okay? So the very first thing that we're going to do, so we've got our sample proportion. That was just finding the mean of a 1, 0 variable. Now, technically, if I wanted to, I could have counted up, or actually here, I could have used that sum function, because if I select this entire column, it's just going to add up all these values. And so all the ones represent the number, someone who did use an e-cigarette. So let me go to the top so we can see what I'm doing here. So this should be, why is that not showing? Oh, hold on. Must have accidentally hit something. So let's do sum of this column. There we go. So this is the number of people in this data set that have ever used. I could divide that by this total sample size, and I should get that same value, right? So just two different ways of doing the same thing. Now, when I'm looking at test statistics for proportions, the equation is pretty similar to what we were doing before. It's a little bit different. I'll take my sample proportion, subtract the assumed true proportion, and then here I'm dividing by the standard deviation of my sample proportions, which we said was the square root of whatever the population portion is assumed to be, times 1 minus that, divided by our sample size. So once again, there's no built-in function here in Excel, but we can use it to be a calculator. So here I'm going to take my sample proportion, subtract the assumed true proportion, divide it by the square root of that assumed true proportion, times 1 minus that assumed true proportion, divided by my sample size, okay? Now, I always like to set it up. I'll show you at the end here. In this one, I always like to set it up putting the hypothesized true value in here, because if I want to change it, then I just have to change it in one spot. I don't have to like find out where, in the formula where it was. So I'll hit enter here. I get 2.41, right? So I did find sample evidence that was going against the null, but does it go against it enough to be able to reject? And here, I actually don't have these lining up. I think I was playing around with this. Let's say I want to be able to reject at the confidence level of 90%, so my alpha is 0.1, okay? Excuse me. So with a right tail test, I found this test statistic of approximately 2.4. For a right tail test, only evidence on the right goes against the null, so the probably I saw sample evidence that was as inconsistent with the null as what I found, or anything more inconsistent, I want this area in the right tail, okay? So in Excel, I can use that norm.s.dist function. The problem is when I tell it my test statistic, comma 1, that gives me the area to the left. What did I actually want? The area to the right, but the area under the curve is 1, so just 1 minus that. Okay. There's my p-value. So once again, I can use that if statement. If my p-value is less than alpha, comma, but the word reject. If it's not, then I should be failing, whoops, to reject, right? This is just our kind of general rule. We reject as long as that p-value is less than alpha, okay? Now, I could also done the critical value approach here. So with my critical value approach, I want to find what's the critical value that gives me alpha total in that right tail. So our alpha was 0.1. So we're working in reverse now. So in Excel, anytime we're working kind of in reverse where we know the area in the tail, we can think of this as our inverse functions. So norm.s.inv, I tell it, okay, I wanted this area in the tail. The problem is if I do this, I'm actually looking up an area of 0.1 in the lower left tail. So I'm going to find the correct critical value, but it's going to be negative. So I can do two different things. I can say, okay, look, I know that if I simply tell it alpha, I'm actually looking at 0.1 in the lower left tail, not the upper right tail. So I can just take the absolute value. It's a symmetrical distribution. It'll give me the right value, but it'll be negative. Okay, so now I've got my positive critical value that makes sense for a right-tailed test. I could also do norm.s.inv. And so, okay, I want 0.1 as the area in my upper right tail, which would mean that the area to the left of that value would be 1 minus that, or 0.9. Sure enough, I get the same value here. Okay. And then here it's a little bit easier because we're looking at a right-tailed test. I don't have to worry about kind of thinking about my absolute value. I just say, is that test statistic greater than my critical value? If it is, put the word reject. If it's not, put the word fail to reject. Okay. Hit enter. Should get the same decision. Now, I wanted to play around with it. So, okay, I can reject at the 90% level. What about the 99, right? So alpha is 0.01. Oh, I actually can still reject at that level. Well, what if I wanted to do what? 0.001? Now I fail to reject, right? So you can play around with this. The other thing I want to say, okay, I can reject 0.75, right? That the true proportion is less than or equal to 0.175. What about 0.18, right? So I still would have evidence that's inconsistent with the proportion being less than or equal to 0.18, but not very much different. Sure enough, I can't reject that value, right? But I can reject 0.175. Okay. Oh, let me think if there's anything else I want to say here with these proportion examples that should cover it. I should have then one other type of test, which is a left-tailed test in our final example. So similar data, this was like ever used, how many days have they tried things. So I think here I was going to look at the age at which they actually, let's see, what column? Yeah, age at which they first tried. I'm remembering this correctly. So I kind of skipped some of the easy stuff here. You know, the sample mean, we just use the average function. Sample size, we use that count function. Now my sample variance, now I'm looking at an example where I'm wanting to do some hypothesis testing about the assumed true mean, but I only have a sample variance. So here, I'm using that var.s to calculate my sample variance. Right? Now, I've got a left-tailed test because my alternative is that the average age is less than 14. So I assume the opposite is true, which is that it's greater than or equal to 14. And we'll actually get this to match up here. I'll play around with this and change it after the fact. 90% confidence level, we've got alpha of 0.1, right? Now we can always change this if we want to. Here I've got my test statistic equation in here. I'm going to use it to kind of point something out. Well, look at this test statistic. This is pretty wild if we're really looking at these values. So the reason why is because it's got a pretty high sample size. right? So that high sample size is really going to reduce that standard deviation, meaning that even finding evidence that's a little bit away from my assumed true value, it's going to be a lot of standard deviations away. Right? So we'll hit enter here. I've got a pretty large test statistic. I'm going to, instead of 14, just to make this a little bit more interesting, what value did I have in here before? I think I did 13.7, oops, sorry, 13.75. Yeah, let's do that. And I'll change this to kind of match it, just so we get something that's a little bit more practical, a little bit more interesting when we start getting into these later results. So there we go. So how did I find my test statistic? My test statistic now, because I only have a sample variance, is going to be coming from the student t-distribution. It's the same setup though. I take my mean, subtract the assumed true mean, divide by the sample standard deviation of my sample means, which is just the square root of my sample variance over my sample size. So I can get these kind of entered in pretty easy. I'm just using Excel to be my calculator here, and I'll reproduce this. So we're just going to take my sample mean, subtract the assumed true mean, divide that by the square root of my sample variance divided by my sample size. Hit enter, it'll close the parentheses for me, and I get negative 0.07 approximately. So now when I'm thinking about for a left-tailed test, from a student t-distribution, where the test statistic I found was negative 2.07, well, evidence that goes against the null now is evidence on the left side, or less than this assumed true value. Remember, these student t's come from this distribution of my sample means, right, where should be centered around whatever that assumed true mean is. Okay. So I want, for a left-tailed test, the area to the left of my test statistic. This is evidence that goes against that assumed true mean or anything even further. But now if I found evidence over here, well, it actually supports the null. So I don't have a two-tailed test, just a one-tailed test. So I'm going to use that built-in t.dist function. So it's just like what we're doing with the standard normal distribution, but instead of norm.s.dist, I'm using t.dist. Okay. So I tell it my test statistic, comma, what are my degrees of freedom? Well, my degrees of freedom are my sample size -1, comma, do I want it to be cumulative? Yes, I want the area to the left. That represents my p-value. Now I'm done, right? Well, I'm done finding the p-value. I could do my rejection decision if that p-value is less than alpha, comma, put the word reject. If it's not, put the words fail to reject. Okay? It's the same setup over and over, right? Doesn't matter the type, this step is the same for every single type of hypothesis test. It's just calculating the test statistic, and when finding the p-value, what distribution am I using? Those are the only things that change, okay? Now, if I want my critical value for a left-tailed test, that's going to be, I can get my fingers to work here. It's going to be, okay, what t-value would give me a total of alpha in this tail? So for a left-tailed test, I know that my critical values, my student t-distribution is centered around 0. It's going to be a negative value. But I know the area in the tail I want is going to be alpha. So similar to what we did before, instead of norm.s.inv, we use t.inv. And I tell it I want alpha in that tail, my degrees of freedom, sample size -1. That lets it know which student t-distribution to use. And I get my critical value. Now you'll notice, and once again, I can, well, before I do this, I can also use okay, if that test statistic is greater in absolute value than my critical value, right? So now I'm thinking about, I'm dealing with negative values. I actually am looking for something that's more extreme or larger in absolute value. So with the left-tailed test, I need to say, okay, is the absolute value of my test statistic greater than the absolute value of my critical value? So is it larger in magnitude? If it is, it's in the rejection region. Put in the word reject. If it's not in the rejection region, put in the words fail to reject. And close my parenthesis for me. So we kind of notice here I'm thinking about, is my test statistic in this range, right? Here's my rejection region. And so what I'm really checking for here is my absolute value of my test statistic, greater than the absolute value of my critical value. If it is, I can reject. Okay. All right. So a couple more things I just wanted to point out, if some of these problems had changed a little bit. But, you know, at this point, I can say, okay, I can reject at the 90% level. What about 99? I can't quite reject at that level, right? My p-value is a little bit larger than that. My critical value now is larger in absolute value than my test statistic, so I can't quite reject at that level of 0.01. Okay. Now you'll notice, even if I go back to doing my alpha 0.1, I found sample evidence that was barely inconsistent with the null, and I can still reject. Why? Because my sample size is so large, right? So, if I was to instead use the norm.s.inv and tell it alpha here, notice these values are really close. But let's just say I only had a sample size of 35 individuals. Well, what is that going to do? If my sample size is getting smaller, this fraction will get larger. I'm dividing by a larger value. Now, my test statistic is going to go down. So going to be less likely I can reject the null. So what is this going to look like? So if I change it to 35, I should now see that the value from the standard normal distribution is going to be a lot different than my student t, right? So anytime you only have a sample variance, we have to use these t.dist and t.inv functions. Now we had a left-tailed test here. One kind of nice option with the student t distribution is, let's say I did want to do a two-tailed test, right? And I wanted to find my critical value. Right? In fact, actually, let's do p-value, critical value. So usually, to find the p-value, would use that t.dist, right? And then tell it your test statistic, it finds the area to the left, right? Now, actually, hold on. I want this to go back to what the actual sample size was. I forgot. Trying to show you too many things at once. There we go. Okay. So usually what I would do is use that t.dist, find the area in the left tail. The only problem is if I had a two-tailed test here. So let's say I'm down here and I've got, I assume it's equal to that value and then not equal to, right? So now I would find the area to the left of my test statistic, but then I would have to multiply it by 2. Remember we did that back in this first example. We just put it 2 times in front of that norm.s.dist function. Excuse me. Same kind of thing we could do with the t.dist, but there's also these built-in options where it just multiplies it by 2 for you. Now, if you're using this, what you have to be careful with is if I try to select this test statistic and then my degrees of freedom would be my sample size minus 1. It's okay. Why isn't it working? Well, the way that the t.dist.2t formula works is it only takes positive values. Right? Well, that's okay because with our test statistic, the area to the left of this negative value, it's going to be the same as the area to the right of this value, but positive. So if you use the .2t option, you'll have to take the absolute value of your test statistic, right? Hit enter. Here's our new p-value. Now, if it's a two-tailed test, and that makes sense, right? It's going to be whatever our p-value was before, but twice as large. But notice, if I find the area to the left and then multiply it by 2, it's really what that 2t function is doing. Okay. All right. And then critical values, let's say I use t.inv. Notice there's a .2t option here as well. So here I'm telling it the total area I want in the tails. So before, when I was doing this with the norm.s.inv function, I kind of had to divide alpha by 2 because I was, wanted half of alpha in each tail. The way that the dot 2t function works is that you tell it the total probability in the tails, comma, here's your degrees of freedom, and it divides alpha by 2 for you, and then kind of looks up those values. Okay. All right. So different ways of doing the same thing. This should kind of cover everything that you need for the Excel homework number 4. This is one of each type of example of hypothesis testing that we talked about. Other than that, should be pretty good. I'll save this file and post it with all the work that we did. I might revert some of it back to like, where was I here? I think I changed the proportion one. Oh no, I changed it back. I'll say I'll had 0.1, 0.0 when we were playing around with different values. I'll make sure everything kind of lines up with where we ended. All right.